A very good morning to our dear lecturer, Dr. Henny. Today, our team will be presenting about the exogenic process and river system for day one and type of rock for day two. So, our team consists of four persons, which is Noel Thomas, me, myself, Cuthbert Savio, Ethan George, and Raibi Izori. So, for the first day, the trip overview, we have visited three locations, which is behind UMS, Jambatan Tamparuli for river system, and Inanam for the folding syncline and anticline. So the weather condition throughout the day is under a warm and humid condition with an average temperature of 28 to 30 degrees Celsius and no rainfall at that day, and river water appeared slightly turbid. The objective of this field trip is to investigate how exogenic process, which is weathering, erosion, transport, and deposition, shape the selected river reach, and investigate type of weathering on site, investigate sites of affected area, and lastly, investigate effect of weathering. So the method that we use is site mapping, which is sketch plan, node channel pattern, bus, cut bank, vegetation, and mark GPS point. So on the first day, on the observation that we had take note, this is at the behind of UMS, physical weathering. This is the close-up of the sedimentary rock. Uh, this indicate the physical weathering, which shows fractured layers indicate mechanical breakdown, fragment and debris suggest erosion and freeze thaw or pressure release processes. Uh, Same with the 4.1.2, the reddish brown rock point to brittle deformation, vein-like intrusion highlight differential weathering between harder and softer mineral. There's also chemical weathering that we can see, which is the extensive oxidation. We can see from the picture that there's a slight difference in color between the rocks, the on the left side and on the right side. Next is biological weathering. Observed feature is active biological weathering. As we can see, uh, the vegetation has grow directly on and around the rock surface. This cause fracture around the rock. Next is erosion. As we can see, the 4.1.6 shows sheet erosion, 4.1.7 real erosion, and 4.1.8 is the gully erosion. As we can see, there's a different size that distinguish between sheet, rill, and gully erosion. Next is observation on the river system. This is overview of erosion on river system. Uh, as we can see, the river have gone have gone through a meandering process, which causes the river to shape like an S shape. And next, structural geology features. This shows cliff face showing folded rock layer with both syncline and anticline formation. As we can see, there's a syncline formation and also anticline formation. My friend Noel will explain the analysis of the each of the physical, chemical, and biological processes.
Thank you, my friend Cuthbert Savio. Now let me continue my part. Firstly, analysis. From our field observation, we see how exogenic processes interact with structural geology features like the syncline and anticline. Together, they form a dynamic river system where tectonic forces set the framework and surface processes continuously reshape it. We move to the physical weathering. The fractured layers and blocky breakdown reveal the stress release, granular disintegration, and freeze-thaw cycles. These loose debris scattered around the site shows active detachment, supplying sediment for river transport, and lithological contrast also play a role. Like harder vein intrusion resist weathering, while softer host rock break down more quickly. Now we move on to the chemical weathering. Oxidation of iron-bearing mineral produces a reddish patina, weakening the rock outer shell. This chemical alteration accelerates mechanical breakdown, showing how the chemical and physical weathering reinforce each other. Move on to biological weathering. The roots penetrate fractures, widening the cracks, while microbes and lichen release organic acid that dissolve mineral. Fern and gases growing directly on the rock surfaces highlight how the biological agent exploit weaknesses created by tectonic and weathering process. We move on to the erosional process. The sheet erosion removes the topsoil, reducing the fertility and exposing the subsoil, while the real erosion marks the transition of channelized flow, accelerating the soil loss. The gully also represent an advanced erosion. The gullies fragmenting the ecosystem and destabilizing the slope. Finally, we have the river meandering. The river meandering demonstrates the dynamic equilibrium, the erosion at cut banks, deposition at point bars, and eventually oxbow formation. Now we go to the structural geology features. First is syncline. Syncline with their true-like geometry trap moisture, promoting chemical weathering and vegetation growth, while the anticline, as elevated structure, accelerate the erosion and the shape, drainage, and slope dynamic. Together, folding highlight tectonic compression and its influence on the landscape evolution. We move to the integrated landscape dynamic. Here, we see the feedback loop, like the tectonic folding sets the framework, weathering weakens the rock, erosion mobilizes the material, and deposition reshape the flood plains. The landscape evolves through continuous adjustment between tectonic forces and exogenic processes. In the broader implication, environmentally, the soil loss reduces resilience, gullies fragment habitats, and man migration alter floodplain hydrology. Geomorphologically, oxbow lakes may form gullies represent irreversible degradation, and folding highlights tectonic control. Management is critical; vegetation cover and contouring prevent the sheet and real erosion. Checks the dam and revegetation stabilize the gullies, and monitoring meander migration support infrastructure planning. In conclusion, the river environment is shaped by both tectonic forces and exogenic processes, weathering erosion, transport, and deposition weakens the rocks and reshape the floodplain, while syncline and anticline reveal the tectonic compression. Guiding these processes together, they create a dynamic environment, vulnerable to degradation but rich in insight but conservation, hazard mitigation, and sustainable land management. That's all for the day one. Now we move on to the day two. Thank you.
Hello, my name is Ethan George. I'm from Group 6 and I will be presenting about serpentinite and peridotite. This slide shows the key features of serpentinite and peridotite, which are closely related rocks but form under different conditions. Serpentinite is a metamorphic rock that usually appears green to dark green, sometimes with a smooth or slightly shiny surface. It is relatively soft with a Mohs scale of 2.5 to 4, and it often feels slippery or fibrous due to serpentine minerals. Serpentinite forms through a process called serpentinization, where peridotite reacts with water. This rock is important because it records mental processes and can contain economically valuable elements such as nickel and chromium. Peridotite, on the other hand, is an ultramafic igneous rock derived directly from the Earth's mantle. It is dark, coarse-grained, and much harder than serpentinite. Its main minerals are olivine and pyroxenes, with chromite sometimes present. Peridotite typically has a phenolitic texture, meaning its crystals are visible and to the naked eye. It forms in the upper mantle and is brought to the surface through tectonic processes such as abduction. In summary, peridotite represents the original mantle rock while serpentinite is the altered form produced by hydration. This slide focuses on the field and geological significance of these rocks. In Ranau Sabah, particularly around Kampung Merakau, both serpentinite and peridotite can be found together. Their presence provides strong evidence of past tectonic activity, including faulting and abduction processes that brought metal rocks to the surface. Studying these rocks helps geologists understand metal processes, tectonic evolution, and fluid rock interactions during metamorphism. The association of serpentinite and peridotite is also characteristic of ophiolite complexes, which represent fragments of oceanic lithosphere emplaced onto a continental crust. From an economic perspective, these rocks are important because they may contain valuable minerals such as nickel, chromium, and chromite. Additionally, serpentinite is significant in engineering and geotechnical studies because its altered nature can affect slope stability and construction safety. To summarize, serpentinite and peridotite are closely related that represent different stages in geological processes. Serpentinite is a hydrated metamorphic rock formed from peridotite through interaction with water, while peridotite is a metal-derived ultramafic igneous rock. Together, these rocks provide valuable insights into metal composition, ophiolite emplacement, and tectonic history. The occurrence in Ranau Sabah makes them especially important for understanding regional geology, as well as mineral resource potential. Overall, the study of serpentinite and peridotite helps us link deep to the earth processes to surface geological features.
Hello, I'm Revi Isori and I'm from Group 6 and I will be presenting about quartz veins or kelerang and phaneretic rock. Phaneretic rock is an intrusive igneous rock with large visible minerals crystal due to slow cooling beneath the Earth's surface. It is hard, dense, and massive with little to no pores. Its minerals include quartz, feldspar, mica, amphibole, pyroxene, and sometimes olivine. An example can be seen at the Tamparuli quarry where magma intruded into sedimentary rocks and cooled slowly. Phanetic rocks are significant because they record past magmatic activity and help us understand crustal evolution. The key feature of quartz vein, it is milky, colorless, or has a pinkish stone. It is also hard and scratch glass and form irregular vein cutting across host rock. Quartz veins are resistant to weathering and mainly composed of quartz with minor feldspar, mica, calcite, or sulfides like pyrite. Quartz veins form from a silica-rich hydrothermal fluid that moves through fractures. As the fluid cools or pressure decreases, quartz crystallizes gradually, filling the cracks. These veins cut across the host rocks, indicating they form after it solidified, and they show past tectonic stresses and fluid movement. For the field localities and geological significance is the phaneretic rocks is observed at Tamparuli Quarry, and for the quartz veins, it is observed in Kampung Kina, Pulidan, Ranau. The phaneretic rocks indicate intrusive magmatic activity, whereas quartz veins show hydrothermal fluids flow along fractures. Both help us understand geological history, tectonic evolution, and potential mineralization in the region. In summary, phaneretic rocks are coarse-grained, intrusive rocks from slowly cooled magma, and quartz veins are hydrothermal silica deposits in fractures. Together, they provide field evidence of magmatic, tectonic, and hydrothermal processes. Tamparuli and Ranau are key examples that highlight Sabah's complex geology.